Tonight, as you drift towards sleep, imagine stepping outside and looking up at the stars. Those distant points of light have watched over humanity for millennia, constant and reassuring in their ancient dance across the heavens. But what if everything you see is an elaborate cosmic illusion? Deep in the halls of theoretical physics, a question whispers that could reshape our understanding of reality itself. It's not the stuff of science fiction nightmares, but a legitimate scientific inquiry that emerged from careful mathematical study. Could Earth, our solar system, perhaps our entire observable universe, exist inside a black hole? This isn't a question born from paranoia or fear. It arose from the elegant equations of Einstein's general relativity, from the same mathematics that predicted black holes decades before we found them lurking in space. When brilliant minds began exploring the deepest implications of space-time geometry, they discovered something unsettling. The mathematics that describes our expanding universe bears an eerie resemblance to the mathematics describing the interior of certain black holes. Picture yourself floating in the vast darkness between stars. From this cosmic perspective, Earth appears as a pale blue dot, orbiting an ordinary yellow star, nestled within the Milky Way galaxy alongside hundreds of billions of other stars. This is the story we've told ourselves about our cosmic address. But what if this comfortable narrative masks a more profound truth? The question isn't whether we're being pulled towards some distant black hole. We know where those cosmic monsters lurk, and thankfully, they're far away. The question is subtler and more disturbing. What if the space we call home, the realm where stars shine and galaxies spin, exists within the event horizon of an incomprehensibly massive black hole? Inside such a cosmic prison, we might never know our true situation. Time and space could be so warped that our instruments, our light, our very perception of reality might be fundamentally deceived. We could be falling endlessly inward while believing we're traveling through open space. This possibility emerged not from wild speculation, but from serious physicists grappling with deep questions about the nature of our universe. They noticed that our cosmos, when viewed from the largest scales, exhibits properties that could theoretically exist within certain types of black holes. The cosmic microwave background, the afterglow of the Big Bang that fills all space, might be reinterpreted as radiation from the event horizon that surrounds us. The implications stretch beyond mere academic curiosity. If we're inside a black hole, then everything we think we know about cosmic distances, the age of the universe, and the fate of reality itself might require fundamental revision. The stars we see might not be separate suns scattered through space, but distorted images created by the extreme curvature of space-time around us. Yet this question, however unsettling, demonstrates the beauty of scientific inquiry. We don't simply accept comfortable assumptions about our place in the cosmos. We test them, probe them, examine them from every possible angle. The same intellectual courage that revealed the true shape of Earth, the motion of planets, and the nature of stars now turns inward to examine our most basic assumptions about existence itself. Tonight, as you rest under those ancient stars, know that human curiosity continues to push against the boundaries of the unknown. Whether we inhabit ordinary space or find ourselves trapped within cosmic horizons, the search for truth continues, guided by careful observation and rigorous thought. Close your eyes and imagine taking a journey outward from where you rest tonight. First, you'd rise above your room, your building, your city, seeing the familiar landscape spread below like a detailed map. Continue upward until Earth becomes a sphere, blue and white and achingly beautiful, suspended in the cosmic dark. This is our home, the third planet from a middle-aged yellow star we call the Sun. Earth maintains its comfortable distance of 93 million miles from our star, close enough to keep water liquid, far enough to avoid being scorched. This distance isn't random. It places us in what astronomers call the habitable zone, where temperature permits the complex chemistry of life. Our planet spins once every 24 hours, creating the rhythm of day and night that has governed life for billions of years. We orbit the Sun once each year, following an elliptical path so stable that ancient civilizations built calendars around its predictability. This cosmic clockwork has persisted for 4.5 billion years, long enough for continents to drift, mountains to rise and fall, and life to evolve from simple cells into the magnificent diversity we see today. Zoom out further, and our solar system reveals itself as a family of worlds. Mercury and Venus huddle close to the Sun's warmth. Mars orbits beyond us, cold and rusty. The giant planets, Jupiter, Saturn, Uranus, and Neptune, patrol the outer reaches, shepherding countless smaller bodies in the asteroid belt and Kuiper belt. This entire system, stretching billions of miles across, represents our local neighborhood in space. But our neighborhood itself moves through something far grander. The Sun, carrying all its planets and moons and asteroids, orbits the center of the Milky Way galaxy. Our galaxy is a vast spiral of 400 billion stars, stretching 100,000 light-years from edge to edge. We're located about halfway out from the galactic center, in a quiet suburban region between major spiral arms. The Milky Way itself belongs to a small cluster of galaxies called the Local Group, which includes the Andromeda Galaxy, slowly approaching us across the cosmic gulf. Beyond this, larger clusters and superclusters of galaxies stretch in every direction, forming a cosmic web of matter separated by vast voids of nearly empty space. This is the story we tell about our cosmic address. It's a tale of nested structures, each level more magnificent than the last. From the atoms in your body to the largest structures in the universe, everything seems to follow comprehensible patterns. Matter clumps into planets, planets orbit stars, stars gather into galaxies, and galaxies cluster across the cosmos according to the patient pull of gravity. The picture feels solid, reliable, based on centuries of careful observation. We've measured the distance to nearby stars using parallax, the tiny apparent shift in position as Earth moves around the Sun. We've weighed the Sun by watching planets orbit it. We've mapped our galaxy by counting stars and measuring their motions. Every measurement fits together in a coherent whole. Yet this comfortable cosmic narrative rests on fundamental assumptions about the nature of space and time. We assume that light travels in straight lines across the universe, that gravity behaves consistently across cosmic distances, that time flows uniformly throughout space. We assume that our instruments measure reality accurately, that our understanding of physics applies everywhere. These assumptions seem reasonable. They've guided us to spectacular discoveries about the cosmos. But what if they're incomplete? What if the very space-time through which we move is more curved, more constrained, more illusory than we realize? What if our comfortable place in ordinary space is itself an elaborate cosmic misconception? The question didn't emerge from a single eureka moment, but grew slowly from the intersection of Einstein's equations and cosmic observations. In the 1970s, physicists began noticing uncomfortable parallels between the mathematics describing our universe and the mathematics describing the interior of black holes. Einstein's theory of general relativity reveals that space and time form a unified fabric that can bend, stretch, and curve in response to matter and energy. This space-time geometry determines how objects move, how light travels, and how time itself flows. The same equations that describe gravity on Earth also govern the extreme physics near black holes and the large-scale structure of the cosmos. When physicists applied these equations to our expanding universe, they found solutions that looked suspiciously similar to the interior of certain black holes. The mathematics suggested that an observer inside a black hole might experience an expanding space, cooling radiation, and the recession of distant objects. Precisely what we observe in our universe. The first serious exploration came from cosmologist Roy Kerr, whose work on rotating black holes revealed that their interiors could contain regions where space expands rather than contracts. Later, other physicists noticed that the cosmic microwave background, the afterglow radiation from the Big Bang, exhibits properties that could theoretically originate from a black hole's event horizon. These weren't wild speculations from fringe theorists. They emerged from mainstream physicists working within established frameworks, following mathematical logic wherever it led. The equations didn't care about human comfort or philosophical preferences. They simply revealed possibilities that demanded investigation. By the 1990s, several research groups had begun exploring what they called the black hole cosmology hypothesis. They weren't claiming Earth sat inside a stellar mass black hole. Such objects are far too small and violent to host planetary systems. Instead, they wondered whether our entire observable universe might exist within a supermassive black hole, perhaps formed in some higher dimensional space we couldn't directly perceive. The idea gained credibility when physicists realized that black holes have thermodynamic properties. They possess temperature and entropy, suggesting they're not just gravitational bottomless pits, but complex systems with rich internal physics. If black holes could have intricate interior structures, perhaps entire universes could evolve within them. Computer simulations revealed that matter falling into certain types of black holes might not simply crush to a point. Instead, it could undergo complex evolutionary processes, potentially giving rise to the kind of space we observe around us. The simulations showed how quantum fluctuations near the event horizon could seed the formation of galaxies and large-scale cosmic structure. The hypothesis received unexpected support from string theory, which suggested that our three-dimensional space might be a projection or hologram of information encoded on a two-dimensional boundary. If our universe is holographic, then the distinction between inside and outside a black hole becomes far more subtle than classical physics would suggest. Leading physicists began taking the idea seriously enough to publish papers in prestigious journals. They developed tests that could potentially distinguish between a universe evolving in ordinary space and one developing within a black hole's interior. The mathematical sophistication of their work elevated the question from philosophical speculation to testable scientific hypothesis. The key insight was that being inside a black hole wouldn't necessarily feel catastrophic. If the black hole were massive enough, billions of times more massive than our Sun, the tidal forces at the event horizon would be gentle. Space and time could appear normal to inhabitants, who might never suspect their cosmic imprisonment. This possibility forced physicists to confront fundamental questions about observation and reality. How do we know we're not already inside such a cosmic trap? What observations could definitively prove or disprove our location within a black hole? The search for answers would require our most sophisticated tools and deepest understanding of the universe. Imagine an object so dense, so gravitationally powerful, that nothing can escape once it ventures too close. Not matter, not energy, not even light itself. This is a black hole, nature's most extreme creation, where the familiar laws of physics stretch to their breaking point and beyond. The story begins with gravity, the weakest of nature's fundamental forces, yet the one that shapes the cosmos on the largest scales. Every object with mass warps the fabric of space-time around it, creating what we experience as gravitational attraction. Earth's mass creates a gentle depression in space-time that keeps us anchored to the ground. The Sun's greater mass creates a deeper well that holds the planets in their orbits. But when matter compresses beyond a critical threshold, something extraordinary happens. The warping of space-time becomes so extreme that it creates a region from which nothing can escape, not because some force prevents escape, but because the very geometry of space and time has been twisted into an inescapable trap. The boundary of this trap is called the event horizon, a spherical surface surrounding the black hole's center. It's not a physical barrier you could touch or see. Instead, it represents the point of no return, where the escape velocity equals the speed of light. Since nothing can travel faster than light, anything crossing this boundary becomes forever trapped. What makes black holes truly mysterious is their invisibility. They emit no light, reflect no radiation, cast no shadow against the stars. We detect them only through their gravitational influence on nearby matter. When gas and dust spiral into a black hole, friction heats the material to millions of degrees, creating brilliant accretion disks that shine brighter than entire galaxies before vanishing beyond the event horizon. The physics inside a black hole ventures into truly alien territory. Time behaves strangely near the event horizon. An outside observer watching something fall in would see it slow down and freeze at the boundary, its image gradually fading and reddening as gravity stretches light to longer wavelengths. But from the falling object's perspective, time flows normally as it crosses the horizon and plunges toward the center. At the heart of every black hole lies what physicists call a singularity, a point where matter reaches infinite density and the curvature of space-time becomes infinite. Here, Einstein's equations break down completely. We simply don't know what happens at a singularity. It represents the limit of our current understanding, a place where quantum mechanics and general relativity must somehow merge into a theory we don't yet possess. Black holes come in different varieties. Stellar mass black holes form when massive stars collapse at the end of their lives, creating objects a few times heavier than the Sun, but compressed into regions smaller than cities. Supermassive black holes, millions or billions of times more massive, lurk at the centers of galaxies, including our own Milky Way. Despite their fearsome reputation, black holes play crucial roles in cosmic evolution. They help regulate star formation in galaxies, drive powerful jets of particles across intergalactic distances, and may have provided the gravitational seeds around which the first galaxies formed in the early universe. The strangest possibility of all is that black holes might not be the cosmic dead ends we once imagined. Some theories suggest they could serve as gateways to other regions of space-time, or even give birth to new universes in dimensions we cannot perceive. The mathematics of general relativity permits such exotic scenarios, even if we lack the technology to test them. Understanding black holes requires abandoning our intuitive notions about space, time, and matter. They exist in a realm where common sense fails, and only mathematical physics can guide us. Yet this same mathematics that reveals their alien nature also governs the gentler space-time around Earth, raising profound questions about the true nature of the reality we inhabit. Picture falling into a black hole, but not the violent, spaghettifying plunge that popular science often describes. Instead, imagine falling into a black hole so massive that crossing its event horizon feels like drifting through empty space. You notice no sudden change, no dramatic boundary, no obvious sign that you've passed the point of no return. This scenario isn't science fiction. It's what physics predicts would happen inside a supermassive black hole, the kind that could theoretically contain entire universes within its event horizon. For such a massive object, the curvature of space-time at the boundary is so gentle that crossing it produces no detectable local effects. Inside this cosmic trap, space could still expand, stars could still shine, and planets could still orbit in apparently normal fashion. The key word is apparently. While everything would seem normal from your perspective inside, the reality would be fundamentally different. You'd be trapped within a region of space-time from which escape is mathematically impossible. The expansion of space inside such a black hole could mimic the cosmic expansion we observe in our universe. As you fall inward, space-time itself stretches, creating the illusion that distant objects are receding from you. This expansion isn't caused by some mysterious dark energy pushing things apart, but by the geometry of space-time inside the black hole, gradually revealing more of its interior structure. Time would flow in peculiar ways within this cosmic prison. From an outside perspective, your entire future history would be frozen at the moment you cross the event horizon. But from your inside perspective, time would continue normally, perhaps for billions of years of subjective experience. You could live entire lifetimes, see civilizations rise and fall, witness the apparent evolution of the cosmos, all while being fundamentally disconnected from the outside universe. The light you'd see would tell a complex story. Radiation trapped inside the black hole with you would continue bouncing around the interior, creating the background glow that might be indistinguishable from cosmic microwave background radiation, light that entered the black hole before you would create the distant galaxies and stars that populate your sky, their images distorted by the extreme curvature of space-time. Even more unsettling is the possibility that reality inside the black hole could be richer and more complex than the outside universe from which you fell. The interior might contain dimensions of space and time that don't exist in the external universe. What seems like empty space around you could be filled with structures and energies existing in these extra dimensions. Quantum mechanics adds another layer of strangeness to the scenario. The event horizon might not be a simple boundary, but a dynamic surface where quantum fluctuations create and destroy particles continuously. These quantum effects could generate the matter and energy that eventually form stars, planets, and life within the black hole's interior. The most profound realization is that inhabitants of such a universe would have no way to discover their cosmic imprisonment through local observations. All their physics experiments would yield consistent results. Their mathematics would work perfectly to describe the phenomena they observe. Their telescopes would reveal a seemingly infinite cosmos filled with countless galaxies. Only by developing extremely sophisticated theories about the large-scale structure of space-time might they begin to suspect their true situation. This scenario forces us to confront the limits of empirical knowledge. If we could be inside a black hole without knowing it, then our most basic assumptions about reality become questionable. The universe we observe might be just a shadow of something far stranger and more complex. The comfortable notion that we inhabit ordinary space becomes not just a hypothesis, but an article of faith, unprovable by any direct observation. The question then becomes whether we have any way to test this possibility, any observation that could reveal our cosmic location with certainty. The seeds of the black hole universe hypothesis weren't planted in philosophical speculation, but in concrete observations that refuse to fit neatly into our standard picture of cosmology. As astronomers peered deeper into space and further back in time, they discovered phenomena that made some physicists wonder whether we might be missing something fundamental about our cosmic situation. The cosmic microwave background proved to be the first puzzle piece. This ancient radiation, discovered accidentally in 1965, fills all of space with a nearly uniform glow left over from the Big Bang. Its temperature is remarkably consistent across the entire sky, varying by only a few parts in 100,000. This uniformity seemed impossible to explain if the universe had always evolved in ordinary open space. The problem is called the horizon problem. Different regions of the early universe, separated by vast distances, shouldn't have had time to exchange energy and reach the same temperature. Yet the microwave background shows they somehow achieved nearly perfect thermal equilibrium. It's like finding that isolated rooms in a house all have exactly the same temperature, despite never being connected. Traditional cosmology solves this with inflation theory, which proposes that space expanded exponentially in the first fraction of a second after the Big Bang. But some physicists noticed that the horizon problem would naturally resolve itself if our universe existed inside a black hole. The event horizon would provide a natural boundary that could maintain thermal equilibrium across the entire interior. The flatness problem provided another clue. Measurements show that the geometry of space is remarkably close to perfectly flat, not curved positively like a sphere or negatively like a saddle. This flatness seems incredibly fine-tuned. In ordinary cosmology, tiny deviations from flatness in the early universe should have grown enormously over time, creating obviously curved space today. But inside a black hole, the interior geometry naturally tends toward flatness as space expands. The same mathematical solutions that describe black hole interiors predict exactly the kind of flat spatial geometry we observe in our universe. The fine-tuning problem disappears if we're already inside a cosmic event horizon. The dark energy mystery added fuel to these speculations. In the 1990s, astronomers discovered that cosmic expansion is accelerating. Something is pushing space apart with ever-increasing force, overcoming the gravitational attraction of all the matter in the universe. This mysterious dark energy comprises about 70% of everything that exists, yet we have no idea what it is. Inside a black hole, apparent acceleration would be a natural consequence of falling deeper into the gravitational well. What we interpret as dark energy driving cosmic expansion might actually be the geometric effect of space-time curvature inside a massive black hole. The acceleration wouldn't require any mysterious new form of energy, just the inevitable consequence of our location within an event horizon. Quantum mechanics offered another suggestive connection. Black holes are known to emit Hawking radiation, a faint glow produced by quantum fluctuations near the event horizon. The temperature of this radiation depends on the black hole's mass. Larger black holes are colder. A black hole massive enough to contain our observable universe would have a temperature of about 2.7 Kelvin, remarkably close to the observed temperature of the cosmic microwave background. The holographic principle, emerging from string theory, suggested that all the information in a three-dimensional volume could be encoded on its two-dimensional boundary. If our universe is holographic, then the distinction between being inside or outside a black hole becomes far more subtle than classical physics suggests. These observations didn't prove we live inside a black hole, but they revealed that the hypothesis could potentially explain several cosmic mysteries simultaneously. The challenge would be finding definitive tests that could distinguish between living in ordinary space and living within a cosmic event horizon. Astronomers have become extraordinarily skilled at finding black holes hidden throughout the galaxy. These cosmic monsters reveal themselves through their gravitational influence on nearby stars and their spectacular feeding displays when matter spirals into their grasp. If Earth existed within a black hole, the sky should show unmistakable signs of our cosmic imprisonment. The nearest known black hole to Earth lies about 1,600 light-years away, a safe distance that poses no threat to our solar system. We detected it by watching its companion star wobble in response to an invisible gravitational partner. The star's motion revealed the presence of an object too massive to be a neutron star, yet producing no light of its own, the telltale signature of a black hole. Throughout the Milky Way, we've catalogued dozens of stellar mass black holes using similar techniques. We watch for X-ray emissions from gas heated to millions of degrees as it spirals toward the event horizon. We look for gravitational lensing effects where black holes bend light from background stars. We search for gravitational waves produced when black holes collide and merge. These detection methods work because black holes in ordinary space create distinctive distortions in their surroundings. If Earth were inside a local black hole, we'd see evidence of the event horizon boundary somewhere in our cosmic neighborhood. Stars and galaxies beyond that boundary would appear distorted, their light stretched and reddened by the extreme curvature of space-time. But when we examine the distribution of stars around us, we find exactly what we'd expect in normal space. The nearest stars show proper motions consistent with their measured distances and velocities. Their spectra display no signs of gravitational redshift beyond what we'd expect from their own surface gravity. Their parallax measurements, tiny angular shifts as Earth orbits the Sun, reveal distances that fit perfectly with our understanding of galactic structure. The Hipparcos and Gaia space missions have measured precise positions and motions for billions of stars throughout our galaxy. Their data reveals the smooth, predictable structure of the Milky Way's spiral arms, stellar populations, and galactic rotation. If we were inside a black hole, these stellar motions would show systematic distortions caused by the curved geometry of space-time within the event horizon. Instead, the stars follow exactly the orbits predicted by Newton's laws and Einstein's corrections for relatively weak gravitational fields. The Sun orbits the galactic center once every 230 million years, maintaining its position within the galaxy's disk through the balance of gravitational forces and rotational motion. This stable galactic orbit has persisted for billions of years, allowing time for planet formation and biological evolution. Observations of the galactic center provide perhaps the strongest evidence that we're not trapped within a local black hole. The supermassive black hole, Sagittarius A star, located 26,000 light-years away, shows all the expected signatures of a black hole in ordinary space. We can track individual stars orbiting this monster, their motions clearly revealing the presence of 4 million solar masses compressed into a region smaller than our solar system. If Earth were inside a different black hole, the view towards Sagittarius A star would be fundamentally distorted. The geometry of nested event horizons would create complex lensing effects and apparent motions that don't match our observations. The fact that we can clearly observe and understand the galactic center black hole proves we're viewing it from outside any local event horizon. Variable stars throughout the galaxy provide another crucial test. These stars pulsate with periods determined by their internal physics, creating cosmic lighthouses whose brightness oscillates on predictable schedules. The timing of these pulsations depends sensitively on gravitational time dilation effects. Inside a black hole, these stellar clocks would run slow compared to their intrinsic rates. But when we observe variable stars, their periods match exactly what stellar physics predicts for their masses and compositions. There's no systematic slowing that would indicate time dilation effects from a surrounding event horizon. Gravity serves as perhaps our most reliable witness to the true nature of space-time around Earth. This fundamental force shapes the motion of every object in our solar system, from tiny asteroids to massive planets, according to laws so precise that we can predict celestial events thousands of years in the future. If Earth existed within a black hole, gravity would behave very differently than what we observe. The curvature of space-time inside an event horizon creates tidal forces and geometric effects that would leave unmistakable signatures in planetary motion, satellite orbits, and even the trajectory of spacecraft we send throughout the solar system. Newton's law of universal gravitation describes how objects attract each other with forces proportional to their masses and inversely proportional to the square of their distance. Einstein's general relativity refines this description, accounting for the curvature of space-time caused by matter and energy. Both theories make precise predictions about orbital mechanics that have been tested countless times with extraordinary accuracy. Consider Earth's orbit around the Sun. For 4.5 billion years, our planet has maintained a stable elliptical path that brings us slightly closer to the Sun each January and farther away each July. This orbital dance creates the subtle variations in solar energy that help drive our seasons, combined with the tilt of Earth's rotational axis. If we were inside a black hole, this orbital stability would be impossible to maintain over geological timescales. Tidal forces within the event horizon would gradually distort planetary orbits, causing them to decay or become chaotically unstable. The precise clockwork of celestial mechanics that has governed our solar system for billions of years simply cannot exist within the extreme space-time curvature of a black hole interior. Our artificial satellites provide even more sensitive tests of gravitational behavior. The Global Positioning System relies on precise timing signals from satellites orbiting Earth at altitudes where they experience slightly weaker gravity than we do on the surface. Einstein's theory predicts that their clocks should run about 38 microseconds faster per day due to both gravitational time dilation and special relativistic effects from their orbital motion. GPS satellites confirm these predictions with extraordinary precision. Engineers must program the satellite clocks to compensate for relativistic effects, or the navigation system would accumulate position errors of several miles per day. This daily confirmation of Einstein's theory provides continuous evidence that gravity around Earth behaves exactly as expected in normal spacetime. The motion of our moon offers another crucial test. Laser ranging experiments bounce light pulses off reflectors placed on the lunar surface by Apollo astronauts and robotic missions. By measuring the round-trip travel time of these laser pulses, scientists can determine the moon's distance to within millimeters. These measurements reveal that the moon is gradually spiraling away from Earth at a rate of about 3.8 centimeters per year. This recession occurs because tidal friction slows Earth's rotation, transferring angular momentum to the Moon's orbit. The rate of recession matches precisely what we'd expect from tidal physics in normal spacetime. Inside a black hole, the extreme curvature would alter these tidal interactions in ways that don't match observations. Spacecraft trajectories provide the most rigorous tests of gravitational physics. When we send probes to other planets, we must calculate their paths through the solar system with incredible precision to ensure they arrive at their destinations. These calculations depend entirely on our understanding of how gravity works in the space around Earth. The success of missions like Voyager, Cassini, and New Horizons demonstrates that our models of solar system gravity are accurate to extraordinary levels. Voyager 1 and 2, launched in 1977, followed complex trajectories that used gravitational assists from multiple planets to reach the outer solar system and beyond. Their successful navigation required predictions of planetary positions and gravitational influences that proved accurate over decades of flight time. The gentle curve of space-time around Earth and throughout the solar system shows none of the extreme distortions that would characterize the interior of a black hole. Light carries messages across the cosmos, and these electromagnetic messengers would tell a very different story if Earth resided within a black hole. Every photon reaching our telescopes has traveled through space-time shaped by gravity, and the nature of that journey reveals crucial information about our cosmic location. When we look at the Sun, we see light that began its journey from the solar surface about 8 minutes ago. This light travels in nearly straight lines through the gentle curvature of space-time in our solar system, arriving at Earth with colors and intensities that reveal the Sun's surface temperature, chemical composition, and magnetic activity. Inside a black hole, light would follow dramatically different paths. The extreme curvature of space-time would bend light rays in complex ways, creating multiple images of distant objects, distorting their apparent positions, and shifting their colors through gravitational effects. We'd see a cosmos fundamentally distorted by the geometry of our cosmic prison. The most obvious signature would be gravitational redshift. Light climbing out of gravitational wells loses energy, shifting toward redder colors. Light falling into gravitational wells gains energy, shifting toward bluer colors. If Earth sat deep within a black hole's gravity well, light from distant stars and galaxies would show systematic blue shifts that don't match what we actually observe. Instead, distant galaxies show red shifts that increase smoothly with distance, exactly as predicted by cosmic expansion in ordinary space. The Hubble-Lemaitre law describes how recession velocity increases linearly with distance, creating a redshift-distance relationship that has been confirmed across billions of light years. This relationship would be impossible to maintain if we were viewing the universe from inside a black hole's event horizon. The cosmic microwave background provides perhaps the most stringent test of light propagation. This ancient radiation has traveled to us from the surface of last scattering, about 380,000 years after the Big Bang, when the universe first became transparent to light. The journey has taken nearly 14 billion years, during which time-space has expanded by a factor of about 1,100. If this radiation were propagating through the interior of a black hole, its properties would be fundamentally altered. The temperature fluctuations we observe in the microwave background, tiny variations that seeded the formation of galaxies and large-scale structure, would be smoothed out or distorted beyond recognition by the extreme space-time curvature. Instead, the microwave background shows precisely the pattern of fluctuations predicted by cosmic inflation in ordinary space. The angular power spectrum, which describes how temperature variations change with angular scale across the sky, matches theoretical predictions with extraordinary precision. This agreement extends across more than 7 orders of magnitude in scale, from the largest observable structures down to the acoustic oscillations that were frozen into the radiation when atoms first formed. Gravitational lensing provides another crucial test of light propagation. When light passes near massive objects like galaxies or galaxy clusters, its path curves slightly, creating distorted or multiple images of background sources. We observe these lensing effects throughout the universe, and they follow exactly the predictions of general relativity for light traveling through ordinary space. If we were inside a black hole, gravitational lensing would behave very differently. The presence of an event horizon would create characteristic caustic patterns and focusing effects that we simply don't see in astronomical observations. The clean, predictable lensing signatures we observe confirm that light is traveling through normal space-time curvature, not through the extreme geometry inside a black hole. Stellar aberration offers yet another confirmation. As Earth orbits the Sun, our motion causes the apparent positions of stars to shift slightly throughout the year. This effect, first observed by James Bradley in the 18th century, depends on the vector addition of Earth's orbital velocity and the speed of light from distant stars. The measured aberration patterns match exactly what we'd expect for Earth moving through ordinary space at the known orbital velocity. Inside a black hole, the relationship between motion and aberration would be modified by space-time curvature in ways that don't match observations. If Earth existed within a black hole, somewhere in our cosmic neighborhood, there would be an edge, an event horizon marking the boundary between our trapped interior and the outside universe. This boundary would leave unmistakable signatures in our observations, creating a cosmic wall that no astronomer could miss. Event horizons aren't physical surfaces you could touch or see directly. They represent the mathematical boundary where the escape velocity equals the speed of light, the point beyond which nothing can return to the outside universe. But while invisible themselves, event horizons create observable effects that would revolutionize our view of the cosmos if they existed in our vicinity. The most obvious signature would be a cosmic redshift gradient. Light struggling to climb out of the gravitational well near an event horizon would be stretched to longer, redder wavelengths. Objects closer to the boundary would appear increasingly redshifted, while objects farther from it would appear less affected. This would create a directional bias in the redshifts of distant galaxies that we simply don't observe. Instead, when we map the redshifts of galaxies across the entire sky, we find a remarkably isotropic distribution. Galaxies in every direction show redshifts that depend only on their distance, not on their location relative to any preferred direction that might indicate a nearby event horizon. This isotropy extends to the cosmic microwave background, which shows temperature variations of only a few parts in 100,000 across the entire sky. If we were inside a black hole, we should also observe systematic distortions in the apparent distribution of matter around us. Gravitational lensing near an event horizon would concentrate light from certain directions while deflecting it from others, creating apparent overdensities and voids in the distribution of galaxies that don't correspond to real material structures. The actual distribution of galaxies around us shows no such systematic distortions. Large-scale surveys like the Sloan Digital Sky Survey have mapped millions of galaxies across billions of light-years, revealing a cosmic web of filaments and voids that extends uniformly in all directions. The statistical properties of this cosmic web match exactly what computer simulations predict for structure formation in ordinary expanding space. Gravitational wave detectors provide another way to test for nearby event horizons. When massive objects accelerate, they create ripples in space-time that propagate at the speed of light. The LIGO and Virgo detectors have observed gravitational waves from merging black holes and neutron stars, revealing that these waves travel through space exactly as Einstein's theory predicts. If Earth were inside a black hole, gravitational waves would propagate very differently. The extreme space-time curvature would alter wave propagation in ways that would be immediately obvious in the detector signals. Instead, every gravitational wave detection confirms that space-time around Earth has the gentle curvature characteristic of ordinary space far from any event horizon. The behavior of light itself provides crucial evidence against nearby boundaries. When we observe distant supernovae, their light curves show the characteristic rise and fall of brightness expected for stellar explosions viewed through ordinary space. The timing of these light curves depends sensitively on how light propagates from the explosion to our telescopes. Near an event horizon, time dilation effects would systematically alter supernova light curves in ways that don't match observations. The most distant supernovae, billions of light years away, show exactly the time evolution predicted for light traveling through expanding space with no intervening event horizons. Perhaps most compelling is the observed homogeneity of physical laws throughout the observable universe. Spectroscopy of distant galaxies reveals that atoms behave the same way everywhere we look. The fine structure constant, which governs electromagnetic interactions, appears to have the same value at every cosmic distance and in every direction. Inside a black hole, the extreme curvature of spacetime could in principle alter fundamental constants or create regions where physics behaves differently. The fact that we see uniform physical laws extending to the cosmic horizon strongly suggests we're observing the universe from ordinary space, not from within any kind of cosmic boundary. Time flows differently in the presence of strong gravitational fields, and this fundamental aspect of Einstein's relativity would reveal itself unmistakably if Earth existed within a black hole. Every clock on our planet, from atomic oscillators to the decay of radioactive elements, would bear the signature of our cosmic location through the warping of space-time itself. Einstein's theory predicts that time passes more slowly in stronger gravitational fields, a phenomenon called gravitational time dilation. We observe this effect in everyday technology. GPS satellites orbiting high above Earth experience slightly weaker gravity than we do on the surface, causing their clocks to tick faster by about 38 microseconds per day. Engineers must account for this relativistic effect, or navigation errors would accumulate rapidly. Inside a black hole, time dilation effects would be far more extreme. Deep within the gravitational well of an event horizon, time would pass much more slowly compared to the outside universe. This difference would show up in every time-dependent process we observe, from the oscillations of cesium atoms in atomic clocks to the periods of variable stars throughout the galaxy. Atomic clocks represent humanity's most precise timekeepers, measuring the natural frequency of electromagnetic transitions in atoms like cesium and hydrogen. These frequencies depend only on fundamental physical constants and should remain constant across space and time. But in the curved spacetime inside a black hole, these atomic frequencies would be systematically shifted compared to their values in flat space. When we compare atomic clocks on Earth with the frequencies of identical atomic transitions observed in distant galaxies, we find remarkable consistency. Hydrogen atoms in galaxies billions of light years away emit light at precisely the same frequencies we measure in terrestrial laboratories, accounting for cosmological redshift effects. This consistency would be impossible if Earth were located in the distorted spacetime inside a black hole. Radioactive decay provides another precise cosmic clock. Elements like uranium and thorium decay at rates determined by nuclear physics, creating isotopic signatures that serve as natural chronometers. The oldest rocks on Earth contain radioactive elements that have been decaying for 4.5 billion years, and their decay rates match exactly what nuclear physics predicts for processes occurring in normal spacetime. If Earth were inside a black hole, the extreme gravitational environment could alter nuclear decay rates through changes in the local structure of spacetime. The fact that terrestrial decay rates match our understanding of nuclear physics, and that meteorites from throughout the solar system show consistent chronological signatures, confirms that we're embedded in the gentle spacetime curvature characteristic of ordinary space. Variable stars throughout our galaxy provide cosmic timekeepers that test general relativity on astronomical scales. Cepheid variables pulse with periods determined by their internal structure and stellar physics. These periods serve as standard candles for measuring cosmic distances, but they also serve as tests of gravitational time dilation. If Earth were inside a black hole, the extreme time dilation would cause all these stellar clocks to appear to run slow compared to their intrinsic rates. We'd observe systematic deviations in Cepheid periods, pulsar timing, and other astronomical chronometers that don't match what we actually measure. Instead, variable stars behave exactly as stellar physics predicts. Pulsar timing is so precise that astronomers use these spinning neutron stars as cosmic clocks to test general relativity and search for gravitational waves. The fact that pulsar periods match theoretical predictions confirms that time flows normally in our cosmic neighborhood. Perhaps most remarkably, the cosmic microwave background carries temporal information from when the universe was only 380,000 years old. The acoustic oscillations frozen into this ancient radiation represent sound waves that traveled through the primordial plasma at precisely the speed predicted by physics. If time were flowing strangely around Earth due to our location inside a black hole, these acoustic signatures would be distorted beyond recognition. The clockwork precision of celestial mechanics provides a final confirmation that time flows normally around Earth. Our planet's 24-hour rotation period has remained stable for billions of years, as recorded in geological deposits and biological rhythms that preserve evidence of ancient day lengths. While Earth clearly doesn't reside within a local black hole, there remains a more subtle and profound question. Could our entire observable universe exist within the interior of an incomprehensibly massive black hole? This possibility, known as the universe as black hole hypothesis, represents one of cosmology's most intriguing and mathematically sophisticated speculations. The idea emerged from careful analysis of Einstein's field equations, which govern the curvature of spacetime in response to matter and energy. When physicists examined solutions describing the interior of black holes, they discovered that some of these solutions bear striking mathematical resemblances to the equations that describe our expanding universe. The key insight is that spatial expansion inside certain types of black holes could mimic cosmic expansion. As matter falls toward the center of a massive black hole, the geometry of spacetime creates the appearance that space is expanding and distant objects are receding. This expansion wouldn't be driven by mysterious dark energy, but would be a natural consequence of the black hole's internal geometry. Such a cosmic black hole would need to be unimaginably massive, perhaps 10 to the 22nd power times heavier than our Sun, to create an interior large enough to contain our observable universe. At this scale, the event horizon would be billions of light-years across, so vast that the curvature of space-time at the boundary would be extremely gentle. Crossing such an event horizon would produce no local effects that inhabitants could detect. The mathematics reveals that inside such a massive black hole, the laws of physics would appear completely normal to interior observers. Stars would shine, planets would orbit, and life could evolve exactly as we observe. The expansion of space, the cosmic microwave background radiation, and even the apparent acceleration driven by dark energy could all emerge naturally from the black hole's internal geometry. This scenario would resolve several puzzles in cosmology. The horizon problem, why distant regions of space have the same temperature despite never being in causal contact, would disappear if our universe began inside an event horizon that naturally maintained thermal equilibrium. The flatness problem would also resolve, since black hole interiors naturally evolve toward flat spatial geometry. Even more intriguingly, the hypothesis could explain the observed value of dark energy. The accelerated expansion we attribute to a mysterious cosmic constant might actually represent the geometric effects of falling deeper into a gravitational well. The acceleration wouldn't require any exotic form of energy, just the inevitable consequence of our location within cosmic event horizon. Quantum mechanics adds additional layers to this picture. The event horizon of a black hole isn't a simple boundary, but a dynamic surface where quantum fluctuations continuously create and destroy particle pairs. These quantum processes might generate the matter and energy that eventually form the stars and galaxies we observe in our cosmic interior. The holographic principle, emerging from string theory, suggests that all information in a three-dimensional volume can be encoded on its two-dimensional boundary. If our universe is holographic, then the distinction between being inside or outside a black hole becomes far more subtle than classical physics would suggest. We might simultaneously exist inside a black hole and yet have all our information encoded on its boundary. Testing this hypothesis presents extraordinary challenges. By definition, observers inside a black hole cannot communicate with the outside universe, so we cannot directly verify our cosmic location. However, some theoretical approaches suggest subtle signatures that might distinguish between a universe evolving in ordinary space and one developing within a black hole's interior. The hypothesis remains highly speculative, representing the frontier where cosmology meets theoretical physics. While mathematically sophisticated and internally consistent, it makes no predictions that differ from standard cosmology in testable ways. It stands as an example of how Einstein's equations permit cosmic possibilities that stretch our imagination while remaining consistent with all known observations. Whether or not our universe exists inside a cosmic black hole, the hypothesis demonstrates the profound depths hidden within the mathematics of space-time and the possibility that reality might be far stranger than our everyday experience suggests. The cosmic microwave background radiation serves as our universe's most ancient photograph, capturing the moment when space first became transparent to light. This faint glow, discovered accidentally in 1965, carries detailed information about cosmic geometry that would reveal unmistakable signatures if Earth existed within a black hole. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into hydrogen atoms. This moment, called recombination, marked the first time light could travel freely through space without being scattered by free electrons. The radiation we observe today has been traveling toward us ever since, carrying a detailed record of conditions at that cosmic moment. The microwave background appears remarkably uniform across the sky, with temperature variations of only a few parts in 100,000. This uniformity initially puzzled cosmologists because regions of space that had never been in causal contact somehow managed to reach nearly identical temperatures. The puzzle deepened when precise measurements revealed that this ancient radiation has a nearly perfect black-body spectrum, indicating thermal equilibrium on cosmic scales. If Earth were inside a black hole, this radiation would tell a completely different story. The extreme curvature of space-time within an event horizon would create systematic distortions in the background radiation that would be immediately obvious to any observer. Temperature patterns would show directional biases pointing toward the black hole's center. The nearly perfect isotropy we actually observe would be impossible to maintain. More subtly, the acoustic oscillations frozen into the microwave background provide precision tests of cosmic geometry. Before recombination, the universe was filled with a hot plasma in which pressure waves traveled at precisely defined speeds. These sound waves created alternating regions of compression and rarefaction that became permanently imprinted in the radiation when atoms first formed. The angular scale of these acoustic peaks depends sensitively on the geometry of space. In flat space, the peaks appear at specific angular sizes determined by the sound horizon at recombination. In curved space, gravitational lensing effects would alter these angular scales in predictable ways. The precise measurements from satellites like WMAP and Planck confirm that space is geometrically flat to extraordinary precision. Inside a black hole, the acoustic oscillations would be fundamentally altered by the extreme space-time curvature. The relationship between sound speed, horizon distances, and angular scales would be modified in ways that don't match observations. The fact that the observed acoustic peaks match exactly what flat space cosmology predicts provides strong evidence that we're observing from ordinary space, not from within any cosmic boundary. The polarization patterns in the microwave background offer additional geometric tests. Light becomes polarized when it scatters off electrons, and the polarization patterns we observe encode information about the density fluctuations and velocity fields present at recombination. These patterns show the swirling and gradient modes expected from primordial gravitational waves and density perturbations evolving in flat space. If our universe existed inside a black hole, these polarization patterns would be systematically distorted by the extreme space-time curvature. The fact that observed polarization matches precisely what inflation theory predicts for ordinary space provides independent confirmation of our cosmic location. Perhaps most remarkably, the microwave background reveals no evidence for any cosmic boundaries or preferred directions in space. If Earth were inside a black hole, we might expect to see subtle gradients or asymmetries pointing toward the black hole's center or the location of the event horizon. Instead, the radiation appears isotropic to incredible precision across all angular scales. The frequency spectrum of the microwave background provides another crucial test. Blackbody radiation has a characteristic shape determined by thermodynamics, but the exact temperature depends on the local gravitational environment. Deep inside a black hole, gravitational redshift effects would alter the observed spectrum in ways that don't match measurements. The observed spectrum matches a perfect blackbody at 2.725 Kelvin, with no systematic deviations that would indicate gravitational effects from a surrounding event horizon. The discovery that our universe is expanding represents one of the most profound revelations in human history, and the nature of this expansion provides crucial evidence about whether Earth could exist within a black hole. The way space itself grows larger, carrying galaxies apart like raisins in rising bread dough, tells a story that would be fundamentally different if we were trapped within cosmic event horizon. Edwin Hubble first noticed in the 1920s that distant galaxies appear to be moving away from us, with more distant galaxies receding faster than nearby ones. This relationship, now called Hubble's law, suggested that space itself is expanding uniformly in all directions. The discovery revolutionized our understanding of the cosmos, revealing that we live in a dynamic universe rather than a static one. The expansion continues today, and remarkably, it's accelerating. In the 1990s, observations of distant supernovae revealed that the expansion rate is increasing over time. Something is driving space apart with ever-growing force, overcoming the gravitational attraction of all the matter in the universe. This mysterious influence, dubbed dark energy, comprises about 70% of everything that exists. If Earth existed within a black hole, this expansion would have a completely different explanation. Instead of space genuinely growing larger, the apparent expansion might result from our motion deeper into the black hole's gravitational well. As we fall inward, the geometry of curved space-time could create the illusion that distant objects are receding from us. However, the detailed properties of cosmic expansion don't match what we'd expect inside a black hole. True expansion, driven by dark energy in ordinary space, creates specific relationships between distance, velocity, and time that have been confirmed through multiple independent observation techniques. The cosmic distance ladder, built from overlapping measurement methods, extends from nearby stars to the most distant galaxies. Each rung of this ladder, parallax measurements, Cepheid variables, type Ia supernovae, and surface brightness fluctuations, confirms that space is genuinely expanding rather than creating apparent expansion through geometric effects. Inside a black hole, these different distance measurement techniques would give inconsistent results. The extreme curvature of spacetime would affect different types of astronomical standard candles in different ways, creating systematic discrepancies that we simply don't observe. The remarkable agreement between independent distance measures confirms that we're observing true cosmic expansion in ordinary space. The age of the universe, derived from expansion measurements, provides another crucial test. If space has been expanding at observed rates, we can extrapolate backward to estimate when expansion began. This cosmic age of about 13.8 billion years matches independently derived ages from the oldest stars, radioactive dating of elements, and the light travel time from the most distant galaxies. Inside a black hole, the relationship between expansion rate and cosmic age would be fundamentally different. The apparent expansion would be an artifact of curved geometry rather than a measure of genuine cosmic evolution. The consistency between expansion-based ages and independent chronological measurements confirms that we're observing real cosmic history unfolding in ordinary space. The cosmic microwave background provides independent confirmation of expansion physics. The acoustic oscillations frozen into this ancient radiation show exactly the pattern expected if space has been expanding and cooling since recombination. The observed relationship between temperature fluctuations and angular scale matches precisely what cosmologists predict for expansion in flat space. Perhaps most telling is the isotropy of cosmic expansion. Galaxies in every direction show redshifts that depend only on their distance, not on their position in the sky. This perfect isotropy would be impossible to maintain if we were falling through the asymmetric geometry inside a black hole. The fact that expansion looks identical in all directions confirms that we're observing from a typical location in ordinary, homogeneous space. Dark energy itself provides evidence against the black hole hypothesis. The acceleration of cosmic expansion requires some form of energy density that remains constant as space grows larger. This violates normal thermodynamics unless dark energy is a genuine property of space itself, not an artifact of curved geometry. The behavior of fundamental particles provides some of our most precise tests of space-time geometry around Earth. Every atomic transition, every radioactive decay, every quantum field fluctuation depends sensitively on the local curvature of space-time. If Earth existed within a black hole, these microscopic processes would reveal the extreme gravitational environment through subtle but measurable deviations from their normal behavior. Particle accelerators have probed the structure of matter and energy to incredible precision, revealing the standard model of particle physics that describes 3 of the 4 fundamental forces. The electromagnetic, weak nuclear, and strong nuclear forces all behave exactly as theory predicts in experiments conducted on Earth, confirming that the local space-time environment matches what we'd expect in ordinary space far from any event horizon. The most precise test comes from the anomalous magnetic moment of the muon, a fundamental property that depends on quantum field fluctuations in the vacuum. Theoretical calculations of this quantity must account for contributions from virtual particles that constantly pop in and out of existence throughout space. These calculations match experimental measurements to more than 10 decimal places, confirming that quantum fields behave normally around Earth. Inside a black hole, the extreme curvature of space-time would modify quantum field fluctuations in ways that would alter fundamental particle properties. The vacuum itself would be fundamentally different, filled with virtual particles created by the intense gravitational fields near the event horizon. These modifications would show up immediately in precision particle physics experiments. Atomic clocks provide another window into particle behavior in curved space-time. These devices measure the natural oscillation frequencies of atoms like cesium and hydrogen. Frequencies determined by the electromagnetic interactions between electrons and nuclei. The incredible precision of modern atomic clocks, they can measure time to better than 1 part in 10 to the 18th power, makes them sensitive to even tiny modifications of fundamental constants. If Earth were inside a black hole, the strong gravitational fields could alter the fine structure constant that governs electromagnetic interactions. This change would show up as systematic shifts in atomic transition frequencies that don't match observations. The fact that atomic clocks on Earth agree with identical atomic transitions observed in distant galaxies confirms that fundamental constants remain uniform across cosmic space and time. Neutrino astronomy provides unique insights into space-time geometry because these ghostly particles interact so weakly with matter that they travel through space essentially unimpeded. Neutrinos from the Sun, from supernovae, and from cosmic ray interactions in Earth's atmosphere all behave exactly as particle physics predicts for propagation through normal spacetime. The IceCube neutrino detector, buried in Antarctic ice, has observed neutrinos that traveled through the entire Earth from the other side of the planet. These particles maintain their quantum properties throughout their journey, confirming that space-time geometry inside Earth matches theoretical predictions. If our planet were embedded in the extreme curvature of a black hole interior, neutrino propagation would be measurably different. Gravitational wave detectors offer perhaps the most direct test of space-time geometry around Earth. The LIGO and Virgo observatories measure tiny ripples in space-time itself, distortions so small they change the length of kilometer-scale laser interferometers by less than 1/10,000th the width of a proton. These detectors have observed gravitational waves from merging black holes and neutron stars, confirming that ripples in space-time propagate at exactly the speed of light with the polarization properties predicted by general relativity. If Earth were inside a black hole, gravitational waves would propagate very differently through the curved interior geometry. The cosmic ray particles that constantly bombard Earth from space provide another test of local space-time properties. These high-energy protons and atomic nuclei travel across the galaxy at speeds approaching light, maintaining their quantum properties throughout journeys that may span thousands of years. When they interact with Earth's atmosphere, they produce cascades of secondary particles that match exactly what particle physics predicts. The consistency of all these particle physics observations confirms that the space-time around Earth has the gentle curvature characteristic of ordinary space in a weak gravitational field, not the extreme distortions that would exist inside any type of black hole. Temperature serves as one of nature's most honest witnesses to cosmic conditions. The thermal environment around Earth carries signatures that would reveal unmistakably if our planet existed within a black hole. Every measurement of cosmic temperature, from the frigid depths between stars to the ancient afterglow of creation, confirms that we inhabit ordinary space far from any event horizon. The cosmic microwave background establishes a universal temperature baseline of 2.725 Kelvin, just a few degrees above absolute zero. This ancient radiation, left over from when the universe first became transparent to light, fills all of space with remarkable uniformity. The temperature varies by only a few parts in 100,000 across the entire sky, representing one of nature's most perfect examples of thermal equilibrium. If Earth were inside a black hole, this thermal story would be fundamentally different. Black holes emit Hawking radiation, a quantum mechanical process that gives them characteristic temperatures inversely related to their mass. A stellar mass black hole with 10 times the Sun's mass would have a temperature of about 6 billionths of a Kelvin, far colder than the observed cosmic background. Conversely, if Earth existed inside a black hole massive enough to contain our local region of space, that black hole would need to be extraordinarily massive, perhaps billions of solar masses. Such an object would have a Hawking temperature of about 10 to the minus 8 Kelvin, again much colder than what we actually observe in the cosmic microwave background. The thermal properties of interstellar space provide another crucial test. Between the stars, space maintains an average temperature of about 2.7 Kelvin, matching the cosmic microwave background almost exactly. Occasionally, regions near hot stars or stellar remnants show higher temperatures, while dense molecular clouds can be significantly colder. But these variations all make sense in terms of local heating and cooling processes operating in normal space. Inside a black hole, the temperature of space would be determined by very different physics. The intense gravitational fields near an event horizon create tidal heating effects that would warm matter and radiation in characteristic ways. The absence of such heating signatures in our cosmic environment confirms that we're not embedded in the extreme space-time curvature of a black hole interior. Stellar temperatures provide independent confirmation of normal thermal physics around Earth. We can measure the surface temperatures of stars throughout our galaxy using spectroscopy, which reveals characteristic patterns of absorption lines created by atoms in stellar atmospheres. These temperatures range from about 2,000 Kelvin for the coolest red dwarf stars to over 40,000 Kelvin for the hottest blue giants. The relationship between stellar color, spectral type, and temperature follows exactly what stellar physics predicts for nuclear fusion processes operating in normal spacetime. If stars were embedded in the extreme gravitational environment of a black hole interior, their thermal properties would be systematically modified in ways that don't match observations. Perhaps most precisely, laboratory measurements of thermal radiation confirm that the laws of thermodynamics operate normally around Earth. Blackbody radiation from heated objects follows Planck's law exactly, with no deviations that would indicate modification by extreme gravitational fields. The fact that earthbound physics matches cosmic observations confirms that we share the same thermal environment as the rest of the observable universe. The absence of thermal gradients pointing toward any cosmic boundary provides another key piece of evidence. If Earth were inside a black hole, we might expect to observe systematic temperature variations that increase toward the black hole's center or show other directional effects. Instead, cosmic temperatures appear isotropic, varying only due to local astrophysical processes. Even the temperature of empty space itself, measured through the zero-point fluctuations of quantum fields, matches theoretical predictions for normal spacetime. The Casimir effect, where quantum vacuum fluctuations create measurable forces between closely spaced metal plates, behaves exactly as quantum field theory predicts in flat spacetime. The thermal signature of our cosmic environment tells a consistent story. Earth orbits through space, where temperature is determined by stellar radiation, cosmic expansion, and local thermodynamic processes, not by the exotic physics that would characterize the interior of any black hole. The graceful dance of galaxies across cosmic space provides perhaps our clearest window into the large-scale geometry of space-time around Earth. These island universes, each containing hundreds of billions of stars, move through space according to gravitational laws that would behave very differently if Earth existed within a black hole. Our home galaxy, the Milky Way, participates in a cosmic ballet with its neighbors that has been choreographed by gravity over billions of years. The nearest large galaxy, Andromeda, approaches us at about 250,000 miles per hour and will merge with the Milky Way in approximately 4.5 billion years. This collision course has been precisely calculated using our understanding of gravitational dynamics in ordinary space. If Earth were inside a black hole, the motion of nearby galaxies would be fundamentally altered by the extreme curvature of space-time. Galaxy trajectories would be systematically deflected by tidal forces and geometric effects that would make the predictable approach of Andromeda impossible to maintain over cosmic timescales. The fact that galactic motions match exactly what Newtonian gravity predicts, with small relativistic corrections, confirms that we're observing from ordinary space. The local group, our cluster of about 80 galaxies, shows patterns of motion that reveal the underlying distribution of matter on cosmic scales. Galaxies within the group orbit their common center of mass, according to gravitational dynamics that have been stable for billions of years. Computer simulations of structure formation reproduce these motions precisely when they assume evolution in ordinary expanding space. Inside a black hole, the local group would exhibit very different dynamics. The extreme space-time curvature would create apparent forces and accelerations that don't exist in the real observations. Galaxy collision timescales would be altered, orbital shapes would be systematically distorted, and the overall evolution of the group would follow patterns that don't match what we actually see. On larger scales, galaxies participate in an even grander structure called the cosmic web. This vast network of filaments and voids extends across hundreds of millions of light years, shaped by the gravitational collapse of dark matter over cosmic history. The statistical properties of this web, how galaxies cluster, how voids are distributed, how filaments connect, all match computer simulations assuming evolution in ordinary spacetime. The cosmic web provides particularly strong evidence against the black hole hypothesis because its structure depends critically on the expansion history of the universe. The observed patterns of clustering could only form if space has been expanding and cooling according to standard cosmology. If we were inside a black hole, the apparent expansion would be an artifact of curved geometry rather than genuine spatial growth, leading to completely different clustering patterns. Gravitational lensing by galaxy clusters offers another test of space-time geometry on cosmic scales. When light from distant galaxies passes through massive galaxy clusters, the gravitational field of the cluster acts like a cosmic magnifying glass, creating distorted and magnified images of background galaxies. The amount of lensing depends precisely on the mass distribution in the cluster and the geometry of spacetime between the cluster and observer. Thousands of galaxy clusters throughout the universe show lensing patterns that match exactly what general relativity predicts for light propagation through ordinary space. The consistency of lensing observations across cosmic distances and redshifts confirms that spacetime geometry remains uniform and predictable throughout the observable universe. If Earth were inside a black hole, gravitational lensing would behave very differently. The extreme curvature of spacetime would create systematic distortions in lensing patterns that would be immediately obvious in cluster observations. The fact that lensing follows standard general relativity predictions provides strong evidence that we're observing from normal spacetime. Perhaps most remarkably, the motions of galaxies reveal the presence of dark matter, mysterious particles that interact gravitationally but emit no light. Galaxy rotation curves, gravitational lensing, and the cosmic microwave background all provide independent evidence for dark matter densities that match precisely across different observation techniques. This consistency would be impossible to maintain if observations were being made from within the distorted spacetime of a black hole interior. After examining evidence from stellar motions, gravitational physics, light propagation, cosmic expansion, particle behavior, thermal properties, and galactic dynamics, we approach the final and most precise measurements that can definitively answer whether Earth exists within a black hole. These observations represent humanity's most sophisticated techniques for probing the fundamental nature of spacetime itself. Parallax measurements provide our most direct method for determining cosmic distances. As Earth orbits the Sun, nearby stars appear to shift their positions slightly against the background of more distant stars. This parallax effect depends only on Earth's orbital diameter and the geometry of space. The European Space Agency's Gaia mission has measured parallax for over 1 billion stars with unprecedented precision, creating the most accurate three-dimensional map of our galactic neighborhood ever constructed. If Earth were inside a black hole, the extreme curvature of spacetime would systematically distort these parallax measurements. The relationship between orbital baseline, stellar distance, and apparent angular shift would be modified by gravitational effects in ways that would be immediately obvious in the data. Instead, parallax measurements match exactly what Euclidean geometry predicts for observations made in flat space, confirming that the local spacetime around Earth has normal curvature. Type Ia supernovae serve as cosmic standard candles, stellar explosions that reach nearly identical peak brightness regardless of their location in the universe. By comparing apparent brightness with known luminosity, astronomers can calculate precise distances to galaxies billions of light-years away. These measurements revealed the accelerating expansion of the universe and provided the first evidence for dark energy. The consistency of supernova distances across cosmic time and space provides powerful evidence against the black hole hypothesis. If Earth were inside a black hole, the extreme gravitational environment would alter light propagation in ways that would make supernova distance measurements systematically incorrect. The fact that these measurements agree perfectly with other distance indicators confirms that light travels through ordinary space to reach our telescopes. Gravitational wave astronomy has opened an entirely new window onto spacetime geometry. The LIGO and Virgo detectors measure ripples in spacetime itself, distortions so tiny they change the length of kilometer-scale laser interferometers by less than 1/10,000th the width of a proton. These measurements confirm that gravitational waves propagate through space exactly as Einstein's theory predicts. If Earth were inside a black hole, gravitational waves would propagate very differently through the curved interior geometry. Wave polarization, propagation speed, and interaction with matter would all be modified in ways that would be immediately apparent in detector signals. The perfect agreement between gravitational wave observations and general relativity predictions confirms that spacetime around Earth has normal curvature. Precision tests of general relativity using lunar laser ranging have measured the distance to the Moon with millimeter accuracy over decades of observations. These measurements confirm that gravitational physics operates exactly as Einstein predicted in the weak field environment around Earth. The gradual recession of the Moon due to tidal friction, the precession of its orbit, and the effects of solar perturbations all match theoretical predictions precisely. Inside a black hole, these precise orbital mechanics would be fundamentally altered by space-time curvature effects. The fact that lunar motion follows standard general relativity with no exotic corrections provides definitive evidence that Earth orbits in ordinary space-time. Perhaps most conclusively, the cosmic distance ladder built from overlapping measurement techniques, parallax, Cepheid variables, surface brightness fluctuations, type Ia supernovae, and the cosmic microwave background all give mutually consistent results for cosmic distances and expansion rates. This remarkable agreement across 10 orders of magnitude in scale would be impossible to maintain if any of these measurements were being made from within the distorted spacetime of a black hole. The precision of modern astronomy leaves no room for the systematic distortions that would characterize observations made from within any type of black hole. Earth orbits peacefully through ordinary space, far from any event horizon. After our comprehensive investigation through the tools of modern astronomy and physics, the evidence speaks with unmistakable clarity. Earth does not exist within a black hole. Every measurement we can make, from the motion of nearby stars to the propagation of light across cosmic distances, confirms that our planet orbits through ordinary spacetime, far from any event horizon. The case against local black hole imprisonment rests on multiple independent lines of evidence that would all need to be systematically wrong for us to be trapped within cosmic boundaries. The probability of such coordinated deception across so many different physical phenomena approaches zero, giving us confidence that our conclusion reflects genuine cosmic reality. Stellar parallax measurements show that space around Earth has normal geometric properties, with no distortions that would indicate extreme space-time curvature. The three-dimensional structure of our galactic neighborhood, mapped through precise position measurements of billions of stars, exhibits exactly the patterns expected for observations made in ordinary space. Gravitational physics operates exactly as Einstein's theory predicts throughout the solar system. Planetary orbits, satellite trajectories, and spacecraft navigation all confirm that gravity behaves normally around Earth, with no exotic effects that would characterize the interior of a black hole. The successful prediction of celestial mechanics over centuries of observation would be impossible if we were embedded in extremely curved spacetime. Light propagation tests reveal that electromagnetic radiation travels through space without the systematic distortions that would be created by a surrounding event horizon. The cosmic microwave background, the redshifts of distant galaxies, and the behavior of starlight all confirm that photons follow the gentle spacetime curvature characteristic of ordinary cosmic expansion. The isotropy of cosmic expansion itself provides perhaps the strongest single piece of evidence against local black hole confinement. Galaxies in every direction show redshifts that depend only on their distance, not on their position, relative to any preferred direction that might indicate a nearby boundary. This perfect uniformity would be impossible to maintain if we were observing from within the asymmetric geometry of a black hole interior. Time dilation tests using atomic clocks, pulsar timing, and variable star observations all confirm that time flows normally around Earth. The precision chronometry that enables GPS navigation and astronomical distance measurements would be systematically affected by the extreme gravitational time dilation present inside any black hole. Particle physics experiments reveal that fundamental constants and quantum field behavior match exactly what we'd expect in normal spacetime. The standard model of particle physics operates without modification around Earth, confirming that the local vacuum has the properties characteristic of ordinary space rather than the exotic quantum environment near an event horizon. Thermal measurements show that space around Earth maintains temperatures determined by stellar radiation and cosmic expansion, not by the Hawking radiation or exotic heating mechanisms that would characterize black hole interiors. The cosmic microwave background temperature of 2.725 Kelvin matches exactly what cosmology predicts for ancient radiation cooling through genuine spatial expansion. Perhaps most remarkably, all these different types of evidence tell the same story. Geometric, dynamical, electromagnetic, temporal, quantum mechanical, and thermal observations all independently confirm that Earth exists in ordinary spacetime. The consistency across such diverse physical phenomena provides overwhelming evidence for our conclusion. This verdict should bring comfort rather than disappointment. We are not trapped within cosmic boundaries, not falling helplessly towards some unknowable center, not cut off from the broader universe beyond. Earth orbits freely through space that connects directly to the vast cosmos we observe through our telescopes. Our investigation demonstrates the power of scientific methodology to answer even the most fundamental questions about our place in the universe. By carefully examining evidence from multiple independent sources and testing predictions against observation, we can determine cosmic truths that transcend philosophical speculation. The universe revealed by this investigation is no less magnificent for being comprehensible. We inhabit a cosmos where light travels freely across billions of years, where gravity shapes the evolution of galaxies and stars, where the laws of physics operate consistently from the smallest quantum scales to the largest cosmic structures. While we can confidently conclude that Earth doesn't reside within any local black hole, a more subtle and profound question remains. Could our entire observable universe exist within the interior of some incomprehensibly massive black hole that formed in dimensions we cannot perceive? This possibility pushes the boundaries of both theoretical physics and human imagination. The universe's black hole hypothesis differs fundamentally from the question we've been investigating. Rather than asking whether Earth sits inside a stellar mass or even supermassive black hole, this idea suggests that everything we can observe, every star, galaxy, and cosmic structure stretching across billions of light years, might be contained within a single, cosmic-scale event horizon. Such a black hole would need to be unimaginably massive, perhaps 10 to the 22nd times heavier than our Sun, creating an event horizon billions of light years across. At this scale, the curvature of spacetime at the boundary would be so gentle that crossing it would produce no detectable local effects. The interior could support the normal physics we observe throughout the cosmos. The mathematical foundations for this possibility emerge from general relativity itself. Einstein's field equations permit solutions where black hole interiors undergo expansion that looks identical to cosmic expansion from the perspective of interior observers. What we interpret as space growing larger due to dark energy might actually be the geometric consequence of falling deeper into an enormous gravitational well. This scenario could potentially resolve several puzzles that have long troubled cosmologists. The horizon problem, why distant regions of space have identical temperatures despite never being in causal contact, would disappear if our universe began inside an event horizon that naturally maintained thermal equilibrium. The flatness problem would similarly resolve, since black hole interiors naturally evolve toward geometrically flat space. Even the mysterious dark energy that drives accelerating cosmic expansion might find explanation within this framework. Rather than requiring some exotic form of energy density that maintains constant value as space expands, the acceleration might simply reflect the geometry of space-time inside a massive black hole. The mathematics works out remarkably well. Quantum mechanics adds intriguing possibilities to this picture. The event horizon of any black hole is a dynamic surface where quantum fluctuations continuously create particle pairs. For a cosmic-scale black hole, these quantum processes might generate the matter and energy that eventually formed all the stars and galaxies we observe. We could be living inside a cosmic womb where quantum creation operates on universal scales. The holographic principle, emerging from string theory research, suggests that all information contained in any three-dimensional volume can be encoded on its two-dimensional boundary. If our universe is holographic, then the distinction between existing inside or outside a black hole becomes far more subtle than classical physics would suggest. We might simultaneously be inside a black hole while having all our information encoded on its boundary. Testing this hypothesis presents extraordinary challenges precisely because it's designed to be observationally equivalent to standard cosmology. By definition, observers inside a black hole cannot communicate with or observe the outside universe. Any test that could definitively prove or disprove our cosmic location would require access to information from beyond our observable horizon. However, some theoretical approaches suggest subtle signatures that might distinguish between a universe evolving in ordinary space and one developing within a black hole's interior. These might include specific patterns in the cosmic microwave background, unusual correlations in large-scale structure, or exotic particle physics effects that could in principle be detected with sufficiently advanced technology. The hypothesis remains highly speculative, representing the intersection of cosmology, quantum mechanics, and string theory, where mathematical possibilities stretch far beyond current experimental verification. Whether true or false, it demonstrates how Einstein's equations permit cosmic realities that transcend our everyday intuition about space and time. Perhaps most importantly, the universe as black hole possibility reminds us that reality might be far stranger and more layered than our current scientific paradigms suggest, while remaining perfectly consistent with all observations we can currently make. The question of whether Earth exists inside a black hole might seem bizarre, even unsettling, but it represents something beautiful about human nature. Our relentless drive to test even our most fundamental assumptions about reality. This investigation reveals as much about the scientific process as it does about our cosmic location. Science progresses not by accepting comfortable truths, but by continuously challenging what we think we know. Every breakthrough in understanding has emerged from someone willing to ask uncomfortable questions, to probe assumptions that everyone else took for granted, to follow mathematical logic even when it leads to disturbing conclusions. The black hole question emerged naturally from Einstein's equations, the same mathematical framework that predicted the existence of black holes decades before we found them lurking throughout the galaxy. When physicists applied these equations to our expanding universe, they discovered unsettling parallels with the mathematics describing black hole interiors. The math didn't care about human comfort or philosophical preferences. It simply revealed possibilities that demanded investigation. This willingness to entertain strange ideas has driven every major revolution in human understanding. Copernicus asked whether Earth might orbit the Sun, rather than sitting motionless at the center of creation. Darwin wondered whether species might change over time, rather than remaining fixed since creation. Einstein questioned whether space and time might be unified and curved, rather than separate and flat. Each of these questions initially seemed absurd, even threatening to established worldviews. Yet by following evidence wherever it led, regardless of philosophical discomfort, scientists gradually constructed more accurate pictures of reality. The process requires intellectual humility, the recognition that our intuitions about the universe might be wrong, our instruments might deceive us, our theories might be incomplete. The black hole investigation demonstrates this scientific humility in action. Rather than dismissing an uncomfortable possibility, we systematically examined evidence from every available source. We tested predictions against observations, looked for systematic biases in our measurements, and remained open to conclusions that might challenge our cosmic comfort zone. This approach has practical benefits beyond satisfying curiosity. The techniques we developed for testing space-time geometry around Earth have applications in GPS navigation, gravitational wave astronomy, and searches for new physics beyond the standard model. The theoretical frameworks we refined help us understand the formation of galaxies, the nature of dark energy, and the fundamental structure of space-time itself. Perhaps more importantly, the investigation illustrates how science builds confidence through convergent evidence. Our conclusion that Earth exists in ordinary space doesn't rest on any single measurement or theoretical argument. Instead, it emerges from the remarkable consistency of evidence across multiple independent lines of investigation. When stellar parallax, gravitational wave detectors, atomic clocks, cosmic microwave background observations, and particle accelerator experiments all tell the same story about local space-time geometry, we can have confidence that our conclusion reflects genuine cosmic reality, rather than systematic error or theoretical bias. The question also highlights the difference between possibility and probability in scientific thinking. General relativity mathematically permits scenarios where observers inside black holes could experience apparently normal physics. But mathematical possibility doesn't imply physical reality. The universe is under no obligation to implement every solution to Einstein's equations. By carefully distinguishing between what's theoretically possible and what's observationally supported, we avoid both excessive skepticism that rejects well-established conclusions and excessive credulity that accepts exotic possibilities without sufficient evidence. This balanced approach has guided science through every major conceptual revolution. The black hole investigation ultimately reinforces our understanding of Earth's precious ordinariness. We orbit through normal space around a typical star in an unremarkable galaxy. This might seem less exotic than residing within some cosmic prison, but it makes us extraordinarily fortunate. Normal space permits the stable planetary environments where life can evolve and consciousness can emerge to contemplate its own existence. The question was worth asking, not because we suspected the answer would be unsettling, but because testing fundamental assumptions strengthens our knowledge and occasionally reveals surprises that reshape our understanding of reality. Our investigation into whether Earth exists inside a black hole has taken us on a journey through modern physics and astronomy that revealed profound truths about both our cosmic location and the methods we use to understand the universe. The knowledge gained extends far beyond the specific question we set out to answer. We discovered that space-time around Earth can be probed with extraordinary precision, using techniques that span from quantum mechanics to cosmology. Atomic clocks measure the flow of time with accuracy better than 1 part in 10 to the 18th power, sensitive enough to detect gravitational effects from elevation changes of just a few centimeters. This precision allows us to test Einstein's predictions about time dilation in Earth's gravitational field on a daily basis. Gravitational wave astronomy emerged as perhaps our most direct probe of space-time geometry itself. The LIGO and Virgo detectors measure distortions in space smaller than 1/10,000th the width of a proton, revealing that space-time around Earth behaves exactly as general relativity predicts. These observations opened an entirely new window onto cosmic phenomena, allowing us to observe black hole mergers occurring billions of light-years away. The cosmic microwave background proved to be our most ancient and comprehensive source of information about universal geometry. This radiation, emitted when the universe was only 380,000 years old, carries detailed information about space-time curvature that has been preserved across nearly 14 billion years of cosmic evolution. Its properties confirm that we observe from a typical location in ordinary expanding space. We learned that multiple independent measurement techniques can provide remarkable consistency when they probe the same underlying physical reality. Stellar parallax, Type Ia supernovae, Cepheid variables, and cosmic microwave background observations all give mutually consistent results for cosmic distances and expansion rates. This convergence across 10 orders of magnitude in scale demonstrates the robustness of our cosmic distance ladder. The investigation revealed how theoretical physics and observational astronomy work together to constrain cosmic possibilities. Mathematical solutions to Einstein's equations permit exotic scenarios like universe-sized black holes, but observations systematically rule out local applications of these exotic possibilities. Theory guides us toward questions worth asking. Observation determines which possibilities reflect reality. We discovered the importance of testing assumptions that seem obviously true. The notion that Earth orbits through ordinary space feels intuitively correct, but science progresses by converting intuition into rigorous proof. By systematically examining evidence for our cosmic location, we transform comfortable assumptions into well-established conclusions. The search taught us to distinguish between local and global questions about cosmic structure. While we can definitively rule out Earth's existence within any local black hole, the possibility that our entire observable universe exists within some cosmic-scale event horizon remains an open question. This distinction between testable and untestable hypotheses helps define the boundaries of empirical science. We learned that precision measurements often provide the most stringent tests of fundamental physics. GPS satellites confirm Einstein's predictions about time dilation to extraordinary accuracy every day. Particle accelerators reveal that fundamental constants maintain identical values across cosmic space and time. These precise confirmations of known physics often provide stronger constraints than dramatic searches for exotic phenomena. The investigation demonstrated how citizen science and international collaboration accelerate scientific progress. The Gaia mission's catalogue of stellar positions and motions required cooperation between dozens of institutions across multiple continents. Gravitational wave discoveries depend on coordinated observations from detectors on different continents. Modern astronomy succeeds through global collaboration that transcends national boundaries. We discovered that comfortable conclusions can be as scientifically significant as surprising ones. Learning that Earth orbits in ordinary space might seem less exciting than discovering we live inside a cosmic black hole. But this ordinary result actually constrains exotic physics theories and confirms our understanding of space-time geometry on cosmic scales. Perhaps most importantly, we learned that the universe becomes more wonderful, not less, when we understand it accurately. The cosmos revealed by our investigation, with its expanding space, ancient radiation, merging black holes, and precisely ticking atomic clocks, possesses a beauty and complexity that exceeds any fictional alternative. Reality, properly understood, surpasses imagination in both its subtle elegance and magnificent scope. While Earth orbits safely through ordinary space, our galaxy harbors genuine black holes whose extreme physics create some of the most violent and energetic phenomena in the universe. These cosmic monsters, scattered throughout the Milky Way and beyond, remind us why we should be grateful for our location far from any event horizon. Stellar mass black holes form when massive stars collapse at the end of their lives, creating objects that pack more mass than our Sun into regions smaller than cities. These cosmic gravitational traps are invisible themselves, but reveal their presence through spectacular displays when matter spirals into their grasp. Gas and dust accelerating toward the event horizon heat to millions of degrees, creating brilliant X-ray sources that outshine entire star clusters. The nearest known black hole to Earth lies about 1,600 light-years away, thankfully far enough that its gravitational influence poses no threat to our solar system. We discovered this cosmic neighbor by watching its companion star wobble in response to an invisible gravitational partner. The star's orbital motion revealed the presence of an object too massive to be a neutron star, yet producing no light of its own. Throughout the Milky Way, astronomers have catalogued dozens of stellar mass black holes using similar techniques. We search for X-ray emissions from accretion disks, gravitational lensing effects that bend light from background stars, and now gravitational waves produced when these cosmic monsters collide and merge with each other. At the center of our galaxy lurks a supermassive black hole called Sagittarius A star, pronounced Sagittarius A star. This cosmic behemoth contains the mass of 4 million suns compressed into a region smaller than our solar system. We can observe individual stars orbiting this monster, their motions clearly revealing the presence of concentrated mass that can only be explained by a supermassive black hole. The Event Horizon Telescope, a planet-sized array of radio dishes working in coordination, has captured actual images of the event horizon shadows of supermassive black holes. These observations of M87 star and Sagittarius A star represent humanity's first direct visual confirmation of event horizons, the boundaries beyond which nothing can escape. Most galaxies appear to host supermassive black holes at their centers, objects millions or billions of times more massive than our Sun. These cosmic giants play crucial roles in galactic evolution, regulating star formation through powerful jets and winds that can heat or expel gas throughout their host galaxies. The masses of central black holes correlate surprisingly well with the masses of their host galaxy bulges, suggesting intimate evolutionary connections. Active galactic nuclei powered by supermassive black holes create some of the most luminous objects in the universe. Quasars, blazars, and radio galaxies all represent different viewing angles and evolutionary phases of the same basic phenomenon: matter spiraling into supermassive black holes and releasing enormous amounts of energy in the process. The jets produced by some black holes stretch across millions of light years, accelerating particles to nearly the speed of light and creating radio lobes visible across cosmic distances. These jets demonstrate that black holes don't simply trap matter and energy. They can also expel it with tremendous force when the geometry and magnetic fields align correctly. Gravitational wave detectors have revealed that black hole mergers occur regularly throughout the universe. When two black holes spiral into each other, they create ripples in spacetime that carry away enormous amounts of energy, more power than all the stars in the observable universe combined, concentrated into fractions of a second. These observations teach us that black holes are dynamic, evolving objects that interact powerfully with their cosmic environments. They grow by accreting matter and merging with other black holes. They influence star formation across their host galaxies. They launch jets that shape intergalactic space. They're far from the cosmic vacuum cleaners of popular imagination. From our safe distance, we can study these extreme objects without experiencing their dangerous effects. We can observe matter compressed to nuclear density, space-time curved to the breaking point, and gravitational fields so strong they dominate the physics across entire galactic centers. These observations test general relativity in regimes where Newtonian physics fails completely. The black holes scattered throughout our cosmic neighborhood remind us that the universe contains physics far more extreme than Earth's gentle environment, while confirming our good fortune to orbit peacefully through ordinary space. As we reach the end of our cosmic investigation, we find ourselves with a deeper appreciation for Earth's remarkable place in the universe. Our planet orbits not within any black hole, but through ordinary space that connects directly to the vast cosmos stretching beyond our imagination. This conclusion brings not disappointment, but wonder at the extraordinary nature of our apparently ordinary cosmic home. Earth maintains its comfortable distance of 93 million miles from the Sun, close enough to keep water liquid, far enough to avoid being scorched. This delicate positioning places us in the habitable zone, where the chemistry of life can unfold across billions of years. We circle our star once each year in an orbit so stable that ancient civilizations built their calendars around its predictability. Our solar system itself occupies a quiet suburban region of the Milky Way galaxy, about halfway between the galactic center and edge. We're positioned between major spiral arms where star formation proceeds at a measured pace, avoiding both the radiation-soaked galactic core and the metal-poor galactic outskirts. This location provides the heavy elements necessary for rocky planets, while avoiding the cosmic violence that characterizes more active galactic regions. The Milky Way belongs to a small cluster of galaxies called the Local Group, which in turn occupies a relatively quiet region of the cosmic web. We're not located in a dense galaxy cluster where frequent interactions would disrupt planetary systems, nor in a cosmic void where galaxy formation struggles against the expansion of space. Our position offers the best of both cosmic environments. Perhaps most remarkably, we exist during a cosmic epoch when the universe is old enough for complex chemistry to develop, but young enough for stars to continue shining brightly. Earlier cosmic eras lacked the heavy elements necessary for rocky planets. Later eras will see most stars burn out, leaving a cold universe of white dwarfs, neutron stars, and black holes. We live during the brief cosmic spring when intelligence can emerge and contemplate its origins. The space through which Earth moves connects seamlessly to the observable universe stretching 46 billion light-years in every direction. Light from the most distant galaxies travels freely across cosmic space to reach our telescopes, carrying information about cosmic history spanning nearly 14 billion years. This connection allows us to study the universe from the scale of atoms to the largest cosmic structures. Our investigation has revealed that this cosmic connectivity extends through every aspect of physics. The same electromagnetic forces that govern chemistry in biological cells also power the fusion reactions in distant stars. The gravitational physics that keeps Earth in stable orbit also shapes the evolution of galaxy clusters across cosmic time. The quantum mechanics operating in terrestrial laboratories also determines the behavior of matter in the most extreme cosmic environments. This unity of physical law across cosmic scales makes scientific understanding possible. We can study stellar nucleosynthesis by examining the spectrum of distant stars, confident that atomic physics operates identically throughout the universe. We can probe the fundamental nature of space-time by observing gravitational waves from black hole mergers billions of light years away. The ordinariness of Earth's cosmic location makes us extraordinarily privileged. We inhabit a stable planetary environment where liquid water can exist for billions of years, where atmospheric chemistry permits complex organic molecules to form and evolve, where geological processes maintain surface conditions compatible with life. Such environments appear to be uncommon in the universe. Our location in ordinary space far from any black hole event horizon means we can observe the universe directly, rather than through the distorted lens of extreme space-time curvature. We can map cosmic history, discover physical laws, and contemplate our place in the grand scheme of existence, because we're positioned where observation and understanding remain possible. The question we began with, whether Earth exists inside a black hole, has led us on a journey through modern physics that reveals both our cosmic location and our cosmic good fortune. We are not trapped within event horizons, not isolated from the broader universe, not victims of cosmic deception. We are free citizens of an open cosmos, connected to the stars through space and time that permit both existence and understanding. In this vast and ancient universe, Earth remains our precious island of complexity, consciousness, and wonder, ordinary enough to be comprehensible, extraordinary enough to be home.